Good morning, students. In our previous class, we have started the nucleophilic substitution reactions of alkyl halides. We will continue with that nucleophilic substitution reaction. Now, our next substitution reaction is substitution of halogen by alkoxy group or conversion of alkyl halide to ether. In this case, we will react alkyl halide Rx with sodium alkoxide and we will heat the mixture. We will get ether plus sodium halide. Now in ether, oxygen is flanked by two alkyl group R and R dash. If R is equal to R dash, that means if both the alkyl groups are same, then the ether will be termed as symmetrical ether. And if R is not equal to R dash, then the ether will be termed as unsymmetrical ether. Now this preparation of ether from the reaction of alkyl halide with sodium alkoxide is referred to as Williamson synthesis. Here we have taken methyl bromide plus sodium ethoxide. When you are heating this mixture, we are getting ether. What is the name of this ether? Methyl ethyl ether, or its UPAC nomenclature is methoxyethane. Let us see the mechanism of Williamson's synthesis. Here we have the Rx. Here see alkyl halide plus OR minus. From where we got this OR minus? From sodium alkoxide. And this OR minus is a strong nucleophile. And we know that this R is delta positive. So this R will invite nucleophile. So OR minus will attack here and Rx bond will be broken. Now, this attack of OR minus to R and the Rx bond breaking will take place simultaneously. That means bond making and bond breaking will take place simultaneously. This happens in SN2 mechanism. We refer SN2 mechanism as a concerted mechanism. So the reaction of Rx with strong nucleophile OR minus will give us ether and halide ion will be the leaving nucleophile. And we know that in SN2, the substrate, here our substrate is Rx, should be unhindered primary alkyl halide. Now let us discuss once again about this Williamson synthesis. Now Williamson synthesis involves the preparation of ether from alkyl halide and alkoxide of sodium or potassium. With the help of Williamson synthesis, we can prepare both symmetrical and unsymmetrical ethers. We know that alkoxides are strong bases or excellent nucleophiles. So their use in ether synthesis will follow SN2 mechanism, and the alkyl halide should always be restricted to unhindered primary alkyl halide. Ether can also be prepared from alkyl halides and dry silver oxide. Here we have taken two molecules of alkyl bromide. This alkyl bromide is reacting with dry silver oxide. We are heating the mixture and we are getting here ether plus 2 silver bromide. Now let us solve one problem. How can you prepare ethoxybenzene by Williamson synthesis? Now, what is ethoxybenzene? Now, one H of benzene, if it is replaced by OCH2CH2, that is ethoxy group, then the compound will be termed as ethoxybenzene. Now, we will prepare ethoxybenzene by the action of ethyl bromide on sodium phenoxide. So ethyl bromide plus sodium phenoxide, if we heat this mixture, we will get ethoxybenzene plus sodium bromide. If I ask you, can you prepare anisole using Williamson synthesis? So first we have to know what is anisole. Anisole is methoxybenzene. So what will be its structure? Benzene ring with one OCH3 group. So methyl bromide plus sodium phenoxide, if you heat the mixture, you will get methoxybenzene, which is also termed as anisole. Let us discuss the substitution of halogen by amino group or conversion of alkyl halide to alkyl amines. This alkyl halide, when treated with ethanolic solution of ammonia and heated under pressure in a sealed tube at 373 Kelvin, yields primary amine plus HX. This one is primary amine. See here, nitrogen with this lone pair is connected to one alkyl group. That means the central nitrogen is connected to one carbon. So this is 1 degree amine. Now this 1 degree amine, which is a product of the first step, reacts with another molecule of alkyl halide. Here HX is given out and we get here 2 degree amine. See, this R is getting connected to this nitrogen. Here this nitrogen is connected to 2 alkyl groups. That means it is connected to 2 carbon. So this amine is termed as 2 degree amine. This 2 degree amine further reacts with another molecule of RX and HX is given out, leading to the formation of 3 degree amine. Here the nitrogen is connected to 3 alkyl group. Now this 3 degree amine reacts further with one molecule of RX. Now we know that nitrogen is having lone pair. Now this attacks this R of RX. As a result of this RX bond is broken and we get quaternary ammonium salt. See this nitrogen atom, as it donates the lone pair, so this nitrogen is becoming plus. So the product is a quaternary ammonium salt. Now this reaction of alkyl halides with ethanolic solution of ammonia yielding a mixture of amines is known as ammonolysis. Now we will study the substitution of halogen by alkynyl group or conversion of acetylene to higher alkynes. Let us start with sodium acetylide plus alkyl halide. See here, suppose instead of sodium, if you have H here, then it will be acetylene. So 1 H of acetylene, when replaced by sodium, we call the compound as sodium acetylide. Now sodium acetylide plus alkyl halide will give you a higher alkyne. See this acetylene or sodium acetylide, it contains how many carbon? 1, 2. But this alkyne, this contains more than 2 carbon. So if your starting compound is acetylene, from where we are getting the sodium acetylide, you are arriving to a higher alkyne. Now this higher alkyne reacts further with NaNH2, sodamide. Now this sodamide will abstract this acidic hydrogen from this alkyne and it will give you RC triple bond C minus Na plus ammonia. Now this H of this alkyne is acidic in nature. This is known as acetylenic H. So RC triple bond CH on reacting with sodamide is giving you a carbanion, or you can also term it as a nucleophile. So this nucleophile now attacks this carbon of alkyl halide. Here our alkyl halide is methyl bromide, and we know since Br is electronegative, so this carbon is delta plus, so this carbon will invite nucleophile, and right now we have with us this nucleophile. So this nucleophile is attacking this carbon, and carbon-bromine bond is broken, and we are getting this alkyne. So please note that this alkyne and this alkyne, if you compare, then this alkyne again is having one carbon more than this alkyne. So in this reactions, we are learning how to convert a lower alkyne to a higher alkyne using substitution reaction. Now let us convert acetylene to propyne. So this is acetylene. First we will convert acetylene to sodium acetylide. Now this sodium acetylide will further react with methyl bromide and we will get propyne. See this one, sodium acetylide, methyl bromide. So this Br and this Na will be given out and this place will be occupied by CH3. So we will get propyne. So this is a method of step up of an alkyne. So here we have learned the step up of an alkyne using alkyl halide. So we have completed our discussion of the first type of reaction of alkyl halides, that is nucleophilic substitution reactions. So we have used these nucleophilic substitution reactions of alkyl halides for the conversion of alkyl halides to alcohol, alkyl cyanide, alkyl isocyanide, nitroalkane, alkyl nitrite, ether, amine, and synthesis of higher alkynes from lower alkynes. In our next class, we will discuss the other types of reactions of alkyl halides, which include elimination reaction and reaction with metals. Thank you.